Your potential is limitless. Why settle for human IQ alone? Now you can supercharge it with AI. Welcome to the SuperAIQ Show. We explore the daily news, real trends, no hype, and practical hands-on AI education. Let's build the future together, one impossible dream at a time.
Millions of people interact with large language models every day, experiencing what feels like spontaneous, fluid conversation. But beneath that illusion of thought is a highly specific, rigidly structured mathematical engine. The original transformer architecture, introduced in 2017, relied on two halves, an encoder and a decoder, primarily designed to translate languages. Today, almost every major text-generating AI strips that architecture down to just the decoder half. This decoder-only architecture is strictly autoregressive. That means it only ever does one thing. It predicts a single next token based entirely on the context of the tokens that came before it. This creates an immediate engineering tension. Neural networks are designed to process massive amounts of mathematical data simultaneously in parallel. Human language, however, relies on a strict sequential arrow of time. Words only make sense in a specific order. To see how these models force parallel computation into sequential text generation without looking ahead, we are going to trace a single prompt through the entire causal decoder pipeline. Mapping this exact sequence of operations is the only way to demystify the so-called black box of AI and to understand the physical and computational limits governing these systems. Let's start with a basic input prompt, the quick brown fox. The model cannot read English characters. Through tokenization, utilizing algorithms like byte pair encoding, the raw text splits apart into discrete subword chunks. This balances vocabulary size, allowing the model to handle unknown words by breaking them down into recognizable fragments. Each of these subword tokens is then mapped to a dense numerical vector known as a token embedding. This array of numbers encodes the semantic and syntactic relationships of that specific word fragment. Because the transformer reads all of these vectors simultaneously to maximize processing speed, the data currently contains no inherent concept of word order. The model sees a bag of words, not a sentence. To solve this lack of sequential memory, the architecture utilizes positional embeddings. These positional embeddings act as coordinate data. They are added directly into the original token embeddings, injecting spatial context into the semantic numbers. The raw text has now been successfully translated into a spatial, mathematical format, ready for the multi-head attention block to begin processing. The core engine of the decoder is the multi-head attention block. Here, the combined input vectors are duplicated and projected into three distinct mathematical streams: query, key, and value matrices. The model calculates an attention score for each token by taking the dot product of the query matrix and the key matrix. This creates a grid that measures how relevant every word in the sequence is to every other word. But text generation requires predicting the unknown. The model cannot use data from future tokens to determine the context of current tokens. To enforce this rule during simultaneous computation, the architecture employs a causal mask. This mask modifies the attention grid by forcing the scores of all future token positions to negative infinity, effectively blocking them from the calculation. The grid is then passed through a softmax normalization function. Because the mathematical exponent of negative infinity is 0, all of this masked future positions are permanently converted to absolute 0. Finally, these masked attention scores are multiplied by the value matrix. This final operation yields a new, deeply contextualized representation for each token that is entirely blind to the words that come after it. Masked self-attention allows the hardware to calculate millions of relationships in parallel, while strictly enforcing the unidirectional flow of time required for human speech. This chart maps sequence length against computational cost. It highlights a critical limitation in standard attention. As you add more text, the computing power required scales quadratically, creating an exponential upward curve. If a user inputs an entire book into the prompt, computing relationships between every single token across the document overloads the hardware's memory limits. To bypass this bottleneck, models like Mistral 7B implement a technique called sliding window attention. Instead of calculating attention across the entire historical document, Sliding window attention restricts the calculation to a fixed local sequence of surrounding words. By capping the attention span, the model sacrifices direct calculation of distant context to save massive amounts of compute power. It relies instead on the deep layering of the network to pass that long-range context forward step by step. Even with restricted attention windows, scaling up a model to utilize dozens of parallel attention heads hits a second major barrier: memory bandwidth. To optimize this data transfer, models like Llama 2 use grouped query attention. In a standard multi-head attention setup, every single query head requires its own unique key and value matrix to be actively loaded into memory, which quickly chokes the system during generation. Grouped query attention optimizes this architecture. It forces groups of query heads to link to a single shared key and value matrix. This configuration slashes the memory overhead required to run the model, drastically improving generation speeds while maintaining high output quality. Beyond optimizing attention, developers continually attempt to increase the sheer parameter count of the feed-forward neural network layers to expand the model's total knowledge. But passing every single token through all 100 billion parameters for every single calculation slows inference to a crawl. The mixture of experts architecture solves this scaling problem. Instead of activating the entire network, a routing mechanism evaluates the token and sends it only to specific, specialized expert pathways. The vast majority of the network remains dormant for that calculation. This sparse activation severs the direct link between total parameter size and processing cost. The model holds massive amounts of latent knowledge, but executes calculations at the speed of a much smaller system. After the data passes through the optimized attention and feed-forward layers, the architecture prepares to output human-readable text. This chart illustrates the final linear projection. The model expands that deeply processed vector into a massive probability distribution, scoring thousands of individual vocabulary words on how likely they are to follow the sequence. At this exact point, user-defined sampling parameters like temperature and top P intercede. These parameters control the selection logic. They dictate whether the model strictly chooses the highest probability word for a logical response, or occasionally selects lower probability words to inject variance. The sampling algorithm makes its final calculation, mathematically locking in a single output word. This is where the autoregressive mechanism completes its cycle. That newly generated token is appended directly to the end of the original input prompt. That entire newly expanded string of text is instantly fed back into the start of the architecture. The model repeats the entire process, from tokenization to masked attention, just to predict the very next word. This calculation loop executes continuously at blistering speeds, only stopping when it finally generates an end-of-sequence token. By combining strict causal masking to enforce the flow of time, with highly optimized attention pathways to calculate context in parallel, decoder models run this continuous cycle to successfully manufacture the illusion of instantaneous human thought.
Well, that's going to do it for today's SuperAIQ show. Appreciate you listening or watching. As always, please like, comment, and subscribe. Until next time, peace.